we move to the next speaker, and again, very short introduction. Even though Professor Ignacio Grossman is not here, one of his former PhD students is here, and Professor David Bernal Neira is assistant professor at the Davidson School of Chemical Engineering at Purdue University. His interests are systems engineering via classical and quantum optimization for industrial applications. So with that, I'll give it to you.
Thank you, Rodrigo. And well, I have big shoes to fill, right? Ignatius. But anyway, I'm David Bernal, and indeed, although this is the challenges session, how about if I try to frame it as an opportunity session? And I will show how tools and techniques that are very common for process systems engineering can be those enabling us to use quantum computing for interesting applications. I'm David Bernal, and I am the principal investigator of this group, which I named Sequoia, Systems Engineering via Classical and Quantum Optimization for Industrial Applications. It's a mouthful. We have several members already, and I really want to thank the local organizers, because I would say my star postdoc, Zedong Peng, actually did his PhD here at Zhejiang. And it's been a pleasure working with him and with the remaining of my group on several topics. By the way, for those that you don't know, Sequoia is also like a big tree that grows in the western coast of the United States, the largest tree in the world. So you can see me in the middle of one of those, like they are absolutely massive. Anyway, so let's get started. I started working in quantum computing when I was at the NASA Quantum Artificial Intelligence Lab. And we started evaluating how could this technology be useful for different applications. After a couple of years, the American Institute of Chemical Engineers, they reached out to me and to some other folks, and they were like, okay, what is this deal with chemical engineering? Can we use this for chemical engineering? And oh, by the way, my talks usually have a lot of QR codes, so have your phone ready just to start shooting and getting a lot of papers. So basically, we wrote this article on quantum computing for chemical engineering, where although it's a short article, and I recommend you to read that, it took a couple of years just to write 10 pages. Believe it or not, the challenge was to amalgamate all this information for our colleagues. And we found the following. We identified 3 areas in chemical engineering which can be positively impacted by quantum computing in the near term. Those 3 areas are computational chemistry, optimization, and machine learning. And although there is potential for each one of them, there are a lot of challenges to overcome. Along those lines, my group, we started working especially in those 3 topics. So I will try to accommodate for examples that we're working in our team on that. So for optimization, which is obviously closer to let's say my background, we started working together with ExxonMobil and IBM solving routing problems, because this was relevant for the transportation of liquefied natural gas. So for those of you more familiar, for example, with the operations research field, this is a vehicle routing problem with time windows. So by the way, spoiler alert, quantum computers do exist and we can access them. So we can start asking questions such as, how would you formulate an optimization problem such that it could be better solved on a quantum computer? If you have doubts, actually, I think last week or so, we put out a paper in computers and chemical engineering on utilizing modern computational tools for mathematical optimization, which included like some perspective on high performance computing, some perspective on quantum computing. So I do invite you to go through this. The second part is computational chemistry, and in this particular field, although I'm not a computational chemist myself, what happens is that many problems relevant for that field can be posed as optimization problems. So we were using many techniques which might sound familiar for the folks here in the audience: Bayesian optimization, gradient descent, second order derivative information to solve problems there. So I'll show you a little bit more. And in fact, we are already being able to solve with small molecules in quantum computers. Water, nitrogen, chains of hydrogen. This paper actually came out of the archive yesterday. So as we speak, things are coming out, and this is something that we're pretty proud of. Hopefully it will hit a journal soon. Now on the machine learning side, if time allows, I will show you one particular application I'm very excited about, which has to do with image classification for disease diagnosis. And how can this be used on a federated way because of data privacy concerns, basically just helping hospitals being able to diagnose diseases while not sharing their patients' data, because privacy in this kind of application is particularly useful. So, and we have some exciting results. So let's get started. And allow me to give you a very brief introduction to quantum computing. I assume that you don't have it, so let me just speak a little bit about it. There are basically practical and functional differences between what we call classical computers, which are those that don't take advantage of quantum mechanics to do computation, and quantum computers. That's the difference. And the promise is that we can accelerate certain tasks, certain computational tasks. And there are few experimental evidence that support that this is possible. Starting back in 2019 with Google's supremacy paper, followed by 2 papers coming out from China, we can see that there is no hidden physical rule that disallow us from performing computational tasks faster on quantum computers than on pretty much any classical computer. Now, there has been a significant progress in algorithm design, even if we don't have those computers yet built. The rules are fairly clear. People doing this kind of analysis, they have written down algorithms and proofs that support the fact that once people call it fault-tolerant quantum computer, but basically errorless quantum computer is provided to them, they will be able to solve problems way faster, provably faster than any classical alternative. And since then, there is a soup here with hundreds of algorithms pretty much ready to be implemented when these computers come to life. There is a lot of progress in hardware as well. People are trying to realize these computers, basically build them, and there are many competing alternatives out there. None of them is particularly dominant with respect to the remaining ones. It's even arguable that the technology that will allow us to have these fault-tolerant quantum computers might not have been invented yet. But there is a lot of progress being made so far. And we have nowadays computers with hundreds, if not thousands, of quantum bits or qubits. Finally, very interesting, there is a lot of software development on an open source fashion. Basically, you can download from the internet the code that executes the quantum computers that IBM or Google has. So you see there are many opposing forces, and it's a very particular kind of sphere which might resonate a lot with process systems engineering. Recently, we all love to put our codes in GitHub. We like using computers, and we like devising algorithms. So this is very relevant. There has been a lot of progress on this last 40 years of quantum computing, but I would claim that we have not yet achieved the full promise of quantum computation. We're living on a very weird moment where we have medium-sized quantum computers. And these medium-sized quantum computers, they're too small for us to implement these error-correcting schemes. But they are too big, well, they are getting too big for us to be able to simulate them using classical computers. The rules are given, you can write down the equations on your computer and try to simulate this, but it basically explodes because of the dimensionality of the problem. So people have called this the noisy intermediate scale quantum devices era, NISQ era, and we get to play with these devices. So the challenge, the opportunity actually, is how can you make anything useful out of these devices? So when will we have fault-tolerant quantum computers? It would be irresponsible from my side to answer that question. But those folks that are actually putting these computers together, they have roadmaps, they call them, where they have proposed whatever they are delivering in every decade. And so far, for this decade, they have been delivering on time the computers. So right now, I know it's a little bit small, but basically now we have computers with 1,000 qubits. And they all claim that by the end of this decade, we will have fault-tolerant quantum computers. So we better get prepared for this technology to be available. And this is not even accounting for disruptive technology. There was a paper, beautiful one, towards the end of last year that basically changed the landscape and accelerated some of these roadmaps 1 or 2 years. So let's pay attention to this. And again, I told you about these experiments that highlight the physical possibility of us realizing quantum supremacy or quantum advantage. I need to be clear, none of this has been done for industrial applications yet. Basically, they are very tailored problems. So the challenge, the opportunity here is we have some methods that can prove advantage, And we have a lot of applications that require better computational methods. How are we going to bridge them together? Okay, so let's keep going. I would say the chemical industry is privileged in order to take early advantage of quantum computing. That because we do deal with some systems that naturally behave according to quantum mechanics, chemistry altogether. There is already research ongoing, and not only coming from my group, but there are other groups around the world that are already experimenting small-scale examples for chemical engineering applications, for control applications. And some other folks work in resource estimation. They start answering questions such as, how big does the quantum computer need to be for it to solve the practical application that I have at hand? Now, from the group of DPU, they have also released some papers answering questions such as, how can you use it for chemical and biomolecular product design? I do invite you to look into their products. And my main mission is, given that there is a growing interest in this field, we need to be careful in order to avoid confusion and hype. Because if not, this would lead to basically a lack of funding when the results are not as surprising as everyone expects. So we need to fight against the hype, and that's basically my mission right now. So here I will discuss algorithms with potential use in chemical engineering, and I will assume that the computers will grow to the size for me to be able to implement these methods. Ready? Cool. So, very brief introduction. This would be a semester-long class. But basically, the way that people are implementing these quantum algorithms, they use like these music sheets. So time goes from left to right, and each one of these lines, they represent the basic unit in quantum computing, which is a bit that allows for superposition, a qubit. Okay? And then we have these tiny boxes, which are operators. They work similar to logic gates. Therefore, people also call them gates. And then you have wherever each box is intersecting with a line, that box is modifying the state of that qubit. We have boxes that go across a single line, boxes that go across two lines, so we differentiate single qubit and two qubit gates. And basically, you can start applying this kind of operations. At each time step, you should be able to know exactly how that state looks like. And finally, the game is about putting those boxes such that the sequence at the end of the day makes sense. Like it gives you an output that you care about, that solves the problem of application. So that we call a quantum algorithm. And in order for you to basically get some solution out of it, you perform something called a measurement, which basically tells you at the end of the day, 0 or 1 for each one of these lines. Easy peasy. So you might wonder like, okay, how come such an easy framework give us such amazing advantages, like speeding up computational process? And basically there are two ingredients. One of them is that the states that you need to describe at each time step, the dimension where they live, it grows as 2 to the power of n. It grows exponentially fast. So we have some apparent parallelism. That before you perform the measurement, you're doing operations of very high dimensions. And as you might know, operating in high dimensions might allow us to do certain operations faster. That's the first ingredient. The second ingredient, it has to do with probability amplitudes. Basically, it's useful to understand some of these things as waves. So you have two waves that they collide against each other. They can add their amplitudes or cancel each other. And people use this fact because those waves in quantum computing, they have to do with the probability of measuring an output to come up with algorithms basically that maximize the chances of you measuring your solution to the problem. So two simple ingredients that gives already theoretical advantage for quantum algorithms, and there are many examples out there. So some of them for simulation of quantum systems, cryptography, search optimization. The algorithms, they already exist, they have already been proposed. So we are hoping to implement them. And here comes the next slide, which is, okay, how do you solve problems using current quantum computers? Because the computers that we require to implement all these methods, unfortunately for us, they require these circuits to be very wide, meaning to have many lines, to have many qubits, and to be very deep, meaning that this measurement box needs to be very far off for you to be able to implement many operations. Unfortunately, that goes beyond the capabilities of our current computers. In particular, the measurement part, it's complicated because either you are the one performing the measurement or the interaction with the surroundings might, people call it collapse of the quantum system. Basically, if an oxygen molecule goes and hits your chip, it is equivalent for you to perform a measurement. So after that point, there is no quantum advantage that you can reach. And people work a lot in trying to protect this kind of computers in order to perform that computation. So anyway, we require wide and deep circuits, and our current devices cannot do. But, and this is interesting, even if your circuits are shallow, they can represent probability distributions that are challenging to represent using classical normal computers. So what do you do with this? And this will be very amenable to the way that you think. People use something called variational algorithms. So if you have ever trained a neural network, this will sound extremely familiar to you. You have a coprocessor, in the case of the neural network, a GPU, where you are constantly running something that might be faster to run there. In that case, a neural network. You execute something through it and measure a loss. You realize, oh, this neural network is maybe predicting my preference depending on clicks or not. It tends to be at the beginning that it's not very good. And then you do an outer loop, you do a classical optimization to change the parameters of that neural network, and then you go again. And these are the epochs that you do while training a neural network. Everyone, I hope this is clear to everyone. What if you change that GPU with a neural network, with a quantum computer, and one of the circuits that is not very deep, but it's still being able for you to do. Those are called variational quantum algorithms. And this is how we are using quantum computers right now. So it might be clear for some of you in the audience, it's immediate that you are like, oh, I should be able to do this. I trained neural networks before. I know what the stochastic gradient descent means. I could apply some of the methods that I have been working on to do this. And this has very promising cases where those probability distributions are complicated, and those are useful, for example, for computational chemistry or for optimization and machine learning. Okay, I know it's a short talk, so sorry for compressing so much information, but I hope this is going to be useful. So let's visit those three areas and see how we're making an impact here. Optimization, I think, is the most relevant for all of us. I don't need to motivate it. We all care about it, and we want to solve these problems fast. One thing that I need to say straight out of the line is that there is no hope that we can accelerate exponentially challenging optimization problems. If you know what an NP-hard problem is, we have no hope to accelerate those exponentially using quantum computers. Yet, and this community has been actually part of that revolution, we usually don't care about exponential speedups. If we can accelerate our method 20%, it's already a big win for us. So that motivates our work in this kind of systems. So here, we just want to try these methods to accelerate our solutions as much as we can, even if we cannot hope to achieve exponential speed. Okay, so just setting the table. In the review paper, we spent some time classifying optimization algorithms. This is classified according to the nonlinearity of the objective and the constraints and the discreteness of the variable. So you can find your favorite optimization problem in this map. And basically, we highlight two areas. The yellow one, which has linear programming and semi-definite programming. Some folks have already proposed algorithms that whenever we have those error-tolerant quantum computers, we can go up here and implement methods that are in fact exponentially faster than the classical ones. So you might be like, oh wait, aren't you contradicting yourself? And the point is that these problems are already easy for classical computers. They're already polynomially solvable. So in that case, you can prove exponential advantage. That is interesting per se, and the moment that we have a fault-tolerant quantum computer, trust me, I'll be running LPs on that. Now, the other area, this one over here, this QUBO stands for Quadratic Unconstrained Binary Optimization. That problem over there looks very similar to a problem in physics called the transverse field Ising problem. And for that, we have heuristic methods that run on our current quantum computers. They run either on this variational fashion that I was showing you about, or they run on other, like specialized machines called quantum annealers that particularly solve that kind of problem. So that's the set. Now, let me show you a couple examples of what we have done. We're solving this vehicle routing problem. It was a very tiny example, not because we care about this example in particular, but because it was the largest thing we could put on a quantum computer. Single depot, 3 customers, and we started wondering, okay, how would you model this problem for a quantum computer to solve? So we came up with a route-based formulation which would pre-compute the routes and just do like some matching. We came up with an arc-based formulation which would basically denote every single arc that you could connect at every time period. We came up with a sequence-based formulation which came up with like pre-computed the sequences that you could visit, and then you could have all these 3 formulations and start comparing them on a quantum computer. 5 minutes. Okay. This is very similar to many of the work that you do on a regular basis, where you write your optimization problems differently and figure out whether simplex or Kurobi can solve it faster. This is very, there are so many opportunities here because all that knowledge can be directly applied here. So again, we ran all the formulations, we realized that compiling them was different because of sizes and density. We even simulated some of the small examples, and at the end of the day, we came up with these resource estimations, figuring out how big does the quantum computer need to be for me to solve problems of practical interest, in terms here of the time horizon that we were considering. So that's an optimization. Here comes the kicker, which is, obviously, we are used to solve hard problems, computationally hard problems. And in those computationally hard problems, for example, combinatorial optimization, enumeration is hopeless. It's possible, but completely impractical. Do we give up then? The answer is no. We come up with all these decomposition methods, where we basically split our problems in tiny pieces that we can solve with the right tool, and then put together those solutions. Sometimes we even with optimality guarantees. An example is MINOP, right? Mixed integer nonlinear program. So how about if we use these methods to take advantage of our quantum computers? It's up there. We already know how to do this. It's just like the rules of the game change a little bit. So let me show you how we did this. You can reformulate MINOPs directly into this cubo shape. If you have continuous variables, you discretize them. If you have integer variables, you turn them into binaries. If you have nonlinear equations, you can actually turn them into quadratics, and you can penalize constraints. If you do this once, amazing. If you have to do it every time that you want to solve an optimization problem, it gets a little bit boring. So for that, we put together some open source code that if you have Julia optimization problems, it automatically translates this into the shape that quantum computers like it, and we actually do the connection for you. So this is up for grabs. This kind of reformulation is by no means the best way. And here I'm claiming decomposition methods. Some other folks have already worked on it. I have some work in it, which is something I'm very excited about. So I'm trying to put everything in perspective. The software, we put it out there. Long story short, is the best thing out there compared to every single competitor that we have. So just use it, please. If you want to start playing with quantum computing, we provide you the tools to use it in it. For the decomposition method, we had to go a long tour around conic programming, compositive programming, in order to be able to turn these heuristic methods into something that gives you optimality guarantees. I will go very quickly, but we should talk about this if you're interested. Everything is freely available, by the way. Everything is on GitHub if you want to. And long story short, we're winning against Kurobi. We are state-of-the-art when solving, in this case, max split, which is a problem in graph theory, through these kind of methods. Chemistry. We went together with Joel Paulson, which is part of this community. My buddies at NASA, and we were like, oh, Bayesian optimization. That sounds familiar, right? You have an acquisition function, and somehow you know where to sample next. This is a tool used by this community forever. And then I realized, wait a second, in these variational algorithms, am I not trying constantly to find new parameters from a black box function? Can I not use these tools for quantum computing? In fact, we could. And eventually, when we were trying to solve hydrogen molecules, we had to come up with some modifications of Bayesian optimization, but this worked out great. Just to wrap up, the last example I had in machine learning, I ran out of time. Apologies. But basically, we were able to encode medical images into, if you notice this has a neural network, but then a step that is quantum representable. And we had this kind of method that allows you to have different hospitals sharing model updates, not the data itself, and giving us advantage in terms of learning. Here, a couple of results that show, yeah, we're doing great, and whatnot, right? More examples, we saw some other data from Alzheimer's and CT scans of kidneys and everything, and we get similar results. We're able to classify medical images on a private issue with simulated quantum computers. So, conclusions and open questions, 3 areas, each one of them with potential and challenges. I don't have time to read through all of them, but enough time for you guys to take a picture and then we can talk about it later, right? And my invitation for this community is, there is so much to do here. It's such a rich and fertile ground. It's an exciting technology, and in my opinion, is the future. We better work together for this thing. If you want to jump in, we're actually organizing a meeting in Denmark. So if you feel like going to Denmark, you spend some time at DTU, friendly fellas, right before a festival, I think, you should come, and we will discuss about this topics. Oof. Thank you.
So, thank you.